Afternoon, everybody. Okay. Yeah, as always, you can, if you have any questions, you can just type them in the chat, or you can unmute yourself. Okay, so today in the lecture, we're going to finish the slides on high performance computing, which we started last week. And then at the end of the lecture, we're going to start into some new slides you uploaded on transport equations. So basically just getting from a little bit more comfortable with partial differential equations and what exactly the different terms physically are doing when you're solving the equations. Okay, so high performance computing, the last day we had gone through what it is, what a supercomputer is, and we then went on to talk about how we have access to K and Sonic supercomputers. So K from the Irish Centre for High-End Computing, and Sonic is in UCD. I didn't mention, but you may have noticed if you go on to Brightspace under module slides and notes, and then the bottom there's high performance computing. I uploaded a couple of videos. So one is how to get an account on K and Sonic. So there's instructions in these slides, but also it's maybe easier just to watch this short video. It shows which website you go to and how you like apply to get an account. And normally it just takes a day or two. And then how you actually connect to the K and Sonic computers through like a Linux terminal. So then we ended the last day by talking about parallel scaling. Yeah, here. So we kind of discussed how not all problems are that easy to parallelize. So some problems are very easy to split into mini problems. For example, like adding two lists of numbers together. But some problems like sorting numbers are not immediately, if you have multiple processors, it isn't immediately obvious how you can actually speed up that process. Okay, so let's just talk about an OpenFOAM case, how an OpenFOAM case is run in parallel, and some of the concepts here transfer across to running Abacus and Fluent models. So it's useful to just go through the OpenFOAM process first, because it's, let's say, a little bit more manual. You have to manually perform some of the steps to do running in parallel, but that will kind of help you understand what happens with Abacus and Fluent behind the scenes when they're running in parallel. So how do they run in parallel, these different computational mechanics and softwares? So OpenFOAM, Abacus, as is Fluent, I use a method called domain decomposition. So domain decomposition, it means you have your domain, which is your problem geometry, and it's decomposed, which basically means split, partitioned. So for example, this geometry here is flow over a backward facing step. This Pitts daily test case, which we did in Fluent. It's also set up as a tutorial in OpenFOAM. So there's flow coming in at a high Reynolds number from the left, and then it separates here. So you get a big recirculation zone, and there's lots of turbulence. So how does that run in parallel? Well, domain decomposition, if I had 4 CPU cores or 4 processors, I'm going to call them processors, then you could split the case into 4 mini cases indicated by the different colors here. So processor 0, 1, 2, and 3. So you could split this many different ways. And then the idea is essentially, if we're running this in the SimpleFOAM solver in OpenFOAM, 4 different versions of SimpleFOAM are running. One is running on this problem, one's running on this, one's running on this, and one's running on this. So obviously the solution in one part depends on the other part. So in the background, the different solvers are talking to each other, and we're using a method called MPI, or message passing interface. And that's basically how processors talk in parallel. They're sending messages to each other at the boundaries. So the amount of information that has to be sent is typically proportional to the length or the size of this processor to processor boundary. So when you're decomposing a case or splitting it, you normally want to minimize the faces that are shared by processors. Okay, so how do you actually do this? So I'll maybe jump over to the terminal how to do this, but we're going to copy this Pitts daily case. So that case is already set up as a tutorial for SimpleFoam in OpenFoam. So I'm going to copy it into my run directory, and then I'm going to go into it, run block mesh, create a mesh, and then I'm going to run the solver in serial and then run it in parallel. So let me just jump across over here. So let me know if the font is a little bit small. Okay, so I'm doing this in my Mac terminal. I have OpenFoam installed in my Mac terminal rather than jumping across the windows, just because it's easier for me. So I'm going to go copy from my tutorials, incompressible, SimpleFoam, Pits Daily. So this flow over a backward facing step is called Pits Daily because these researchers, Pitts and Daly, set this case up experimentally originally as a benchmark. So I have Pitts Daily here. It's going to run block mesh, create the mesh. I have a shortcut on my Mac called parx, which just opens the case in ParView. So let me just, before I run the solver, open it up so you can see what it looks like. So turn on the mesh. So you can see the case is set up. It has some refinement or grading as well. And so this is like the case running Fluent. So if I then run the solver, SimpleFoam, it runs through a bunch of iterations. So it says time, but SimpleFoam is a steady state solver. So it's basically just iterating, and it stops after 288 iterations. If I type ls, okay, store the final result, but it also stored the result after 100, 200, depending on the settings in control dict. So if I go refresh, skip forward, I should, if I get this far out of the way, I should have the results. So if I look at the velocity field, maybe turn off the mesh, you can see velocity coming in, and you can play and see how it converges in time, but we just want to look at the final converged value. You can look at your pressure, K from K epsilon turbulence model we're using in this case, all of those things, and turbulent viscosity, etc. Okay, so that's fine. That's just running the case in serial. So let me just delete the results. So how do we run this case in parallel? So that only used one processor or one CPU core on my computer. So if I ls system, I'm looking for a file called decompose pardict. So it's not there, there isn't one in that case, but I can copy it from another tutorial which does have a decompose pardict, or they're all stored in one particular place, which is in foam etc. So if you go foam etc / and autocomplete that, there's something called case dicts, and this gives examples of all the different dictionaries you might use in OpenFoam. Yeah, so if we see parallel here somewhere, maybe it's general, I'm not sure where it is. So I'm actually just going to search. So dash name decompose pardict, pre-processing that's under. So if I go copy pre-processing decompose pardict, and then I'm going to put that in my system folder. So Emacs, if I go system decompose pardict, so what does this dictionary do? Well, it's basically going to tell OpenFoam how to split the case to run in parallel. So the top setting, number of subdomains, this is how many subdomains we're going to split our full domain into. So in this case, if it's set to 4, you can obviously set it much larger. If you're running on a supercomputer, you might be running on 40 or 80 or hundreds of subdomains. My i7 only has 4 cores, so I can't set it higher than 4 because it'll just give out and tell me I don't have that many cores. So let's set it to 4. Then the other setting is what method you use to split it. So in this case, you can see it was just split once in the X and once in the Y. So that's using something called a simple method. So you can see the methods are, there's geometric splitting methods, simple, hierarchical. So split in a particular direction, like split 4 times in the X direction and twice in the Y. But then there's other methods like Scotch or Metis, which they are essentially their own software where they split it and try and minimize the number of processors or processor faces. So let me just check. I'm not sure if I have Scotch installed. So I'll try to set it Scotch. If I select Scotch or Metis, I don't need to specify any other options. I just say how many domains. So once I've done that, I have my mesh already created with block mesh. So now I run a utility called decompose par. So maybe I don't have Scotch installed. So let me go back and try Metis and see if Metis is installed. If not, I'll just go back to simple. No, I don't have either of those installed. So I'll just go simple So if I go, by default, they will be installed on your Windows OpenFOAM. It's just I would have manually installed this version on my Mac. So if you specify simple, and you have to specify how many times you're splitting in the X and how many times in the Y. So if I 4, I could split 4 times in the X, and not splitting it Y, so splitting it once in Y and Z. So if I go to compose bar, okay, so it runs now. So what does it print out? It says it's splitting the case, and then it says, well, for processor 0, there's 3,000 cells. Processor 1 is about 3,000. So you can see it's trying to balance the number of cells, which is the computational work for all the processors. And then it's saying how many faces are shared as well. So if I now type ls, you'll see that it created 4 directories: processor 0, 1, 2, 3, and 4. So what are they? They're actually mini OpenFOAM cases. So if I go inside processor 0, it's just a little OpenFOAM case. So in this case, it doesn't have a system folder because OpenFOAM will know to use the folder above. But I can copy that system folder just temporarily if I just wanted to see the case. You normally don't have to do this, but I'm just going to open the case up in PowerView just so you can see it really is just like a mini OpenFOAM case. So this is processor 0. So this corresponds to just the first like quarter of the cells here. So that it is that's where processor 0 will do its calculations. So you can see here's the interface. Yeah, I'll just delete that system folder, and now I just use that for PowerView because PowerView would complain otherwise. Okay, so the way it runs is if I were to run SimpleFOAM now, just like this, that still runs in serial. So if I press Control-C, that would kill it. Let me just delete those results and this post-processing directory. So to actually run in parallel, you have to use a command called MPI run. So MPI run, this message passes interface run. It's basically a separate command. It's not an OpenFOAM thing. It's external to OpenFOAM. It's a way that allows you to start a process multiple times. So when you write SimpleFOAM, it just starts SimpleFOAM once. But if I go MPI run, I can say how many times SimpleFOAM should start. So if I go MPI run -N4, so N4 means number of processes. So SimpleFOAM. And then the last thing is you have to, so that will start 4 SimpleFOAM cases, but you have to tell OpenFOAM or SimpleFOAM that is running in parallel. So you have to go -parallel. If you leave off this -parallel, it will actually just run the case 4 times in serial at the same time. So you have to go -parallel, and -parallel will mean that SimpleFOAM will start. It will know that there's multiple ones running, and they will organize themselves. So one runs in one case, one runs in the next. So if I do that, then in this case it doesn't work because I never actually set that up on my Mac, but I have it in the notes here of what happens. So if you run the command here, so it can be N or NP, it will run the case in parallel. And then after that's finished, you'll see inside the processor directory, you have time directories written. So the results get written to processor 0, 1, 2, and 3. So once they're all written, then if you're in PowerView, you'll have seen this option here, reconstructed case. So by default, it'll read the serial case, but you can actually set that to decompose case, press apply. So in this case, I don't have results because I didn't run it in parallel. But you can see this is actually reading the mesh from the processor directory. So it's reading the 4 different processor directory meshes and visualizing that in parallel. So if you set that to decompose case, you can actually view the results as well. But there's many times you want to reconstruct all the results back into the serial case because for running extra post-processing utilities and things like that. So in that case, once you run it in the solver in parallel, you can run reconstruct par, and that's kind of the opposite of decompose par. So that will run through your processor directories, and it will, if it finds any time results, it will reconstruct those and create the equivalent in the serial case. So in this case, I don't have any results, so I can't do anything. So that's the idea. So I've put some screenshots here just to explain. So that's the general concept of domain decomposition. So you actually have to, in OpenFOAM, like really manually tell OpenFOAM to use multiple processors and how many processors and how how you're actually going to split up the case. So when you run Abacus and Fluent, it's not as manual, but you still need to tell it how many cores you're using. So for example, if you're using Abacus through the GUI, there's a tab which is parallelization, and you can tick how many CPU cores to use. And there's some settings around decomposition you can control. Similarly in Fluent. But most of the time, you won't be really using that option unless you're going to an actual supercomputer. Because if I have a decent i7 and that has 4 cores, but realistically, a couple of those cores are doing something just running my computer. So I probably will only see speed ups of using 2 or 3 cores. So it's not that useful. So it's only when you go to a supercomputer, you want to be running on 20, 40, or hundreds or thousands of CPU cores. And once again, like we said the last day, just because you use more cores doesn't mean that the model will run faster. So at some point, the amount of information being transferred and the time it takes to transfer information between the different subdomains, that takes longer than the amount of time it takes for each subdomain to do their calculations. So that applies to all of these softwares. Okay, so how to sign up for Sonic PK. I said I put a video on Brightspace, but here's short instructions. Basically, you can apply through IT services, and you can tick. There's different clusters you can get access to. There's a few extra things as well. So with Sonic, that's the UCD cluster, which you can run ANSYS and OpenFOAM on, but not Abacus, because they don't have Abacus installed. Then once you get your password and you're ready to go, you can log into the system. But for K, there's an extra step. So K is the bigger computer, and they do have Abacus. So they have an extra layer of security using what's known as an SSH key, or secure shell key. So it's kind of like this, your own private kind of lock and key, which is like in the form of 2 files, and you send them basically the lock for your private key. So once you get signed up, they will send you an email with instructions, and it's explained in the video I uploaded where how you generate this key, and then you have to email it to K. I can't remember the email support that I checked, so it's explained in the video. You have to email it to them, and then they'll install it for you. And once they've confirmed they've done that, then you'll be able to log into the K supercomputer system. Then how to actually log on to them? Well, these systems are running Linux. So as with most supercomputers, they run Linux. So you log in typically through a Linux terminal. So there's a command in Linux called SSH. So that's a secure shell. So it's like an encrypted way to connect from one computer to another computer using Linux. So the general form is you type SSH, your username for that system, whatever that is. So you'll be given one for K, and then for Sonic, it will be your student number. And then Sonic, the address is login.ucd.ie. So you go at login.ucd.ie. So this will try to connect over the internet to that system. Similarly for K, it'll be your K username, that's at k.eject.ie. So for example, I can just show you briefly how that works. So if I want to log into the Sonic system, it's login or pcardiff, which is my username, at login.ucd.ie. So that is not letting me log in at the moment because I'm off campus, but typically it would ask for my password. I've actually set it up though that I can do it through a proxy. So I've created a shortcut called Sonic here, and it connects to another computer first using what's known as a Bastion account, and that's explained in the video as well. But there's some restrictions as to from where you can connect to some of these computers. So in this case, I log on to Sonic and I get this message explained. Welcome to Sonic. If you want documentation, here it is. Here's the hardware, things like that. So then when I'm logged in, I have my own home folder here, and then I can keep all my models here and run different things. So you can see I have random results and stuff. So then I can upload my Abacus, Fluent, or OpenFOAM models to Sonic. Well, for Sonic, they don't have Abacus, but OpenFOAM or Fluent, and I can run them there. And then when I get the results, I can copy down the results that I want to analyze. And then I can just type exit to log off. That's the same idea with K. It'll be SSH. I think it's pcardiff for me as well at k.eject.ie. So I've already sent them my key, and then I have to type the password. So I have a pretty long password here, so I'm not going to type it in because I have to look it up each time. Okay. So that's the idea. Once you connect, then it's just like a Linux system. It's just another Linux computer, and you have your home directory, and you can run things in there. And so here's just some comments on how you can access. If you're from you can access to K from anywhere, from home. But if you're at home and you want to access to Sonic, then you have to go via what's known as a Bastion server. So it's like a proxy server. So there's a way to do that as well. And so some of these are just kind of instructions repeated in the video, and there's different softwares you can you can use to connect. So if you're using Windows, well, it doesn't have a native Linux terminal, so you could fire up your Ubuntu for Windows and just do it from there, or you can download particular software. So there's one called PuTTY, which is a free one, and there's another one called MOBA Xterm, which in recent years I recommend. So I think in a video I explain how to use MOBA Xterm and how to use just your direct Ubuntu terminal. But I think these slides might explain how to use PuTTY a different way to do it. So logging into them, you get a particular message when you log into either one. So how to navigate around different systems. I'm not going to go through the details here, but essentially you're given a home directory for both of them, which you can only store a small amount of data in, so maybe 10 gigabytes or 20 at most. So obviously if you're running big models, you can make an OpenFOAM model that is hundreds of gigabytes if it's like hundreds of millions of cells. So the way they allow for that is they create what's known as a work directory or scratch directory. So they back up your home directory, which is small, but the scratch directory, where there's a particular address, you can have huge amounts of data, terabytes of data there, but they don't back it up. And basically the policy is once you've run your models, then you should clean the results you don't need and copy down the ones, or get rid of the results you don't need. And they do email periodically shaming people who haven't cleaned that out. So they'll put a list of people who haven't cleaned up. So you do have to kind of keep on top of that. And so I won't go through all the details, but one command to mention is the module command. So these systems will have software installed on them, and you can go module space avail, and that will show software that's installed. And then if you want to load particular software, you can go module load, for example, Abacus. So if I go back to Sonic here, log into Sonic, I can go module avail. And so here's all the software that's installed. So you can see they have a OpenFOAM 7. Okay, so it's not that old. So I can go module load OpenFOAM /7. Then it says, okay, to use OpenFOAM, I need to run this command. That's fine. And then once I've done that, if I type block mesh, I think it should work. Yeah, okay. Or block mesh or IcoFOAM, you can see now I'm able to use OpenFOAM. You can install your own software in your own home directory as well, but it requires a little bit more, let's say, Linux experience. Okay, then the last thing to mention is, well, how do I run the jobs? Do I actually just manually type in IcoFOAM there to run the case? Well, no. If you remember at the start of these slides, when I'm logged in there, I'm on what's known as a head node or a login node. So if I want to have access to the hundreds of cores, then I need to submit a script to a queue. So how do I do that? So I have some slides here. Well, how do I copy my models to Sonic or K? But then how do I run an OpenFOAM case in K? I have slides on how you run an OpenFOAM case in Sonic, how to run an Abacus case in K, and how to run an ANSYS Fluent case on K. But then last year they actually added ANSYS Fluent to Sonic, so I haven't added those slides, but it's very similar. You can see that there's a clear pattern how to do this. So I'm just going to go through this, how to run OpenFOAM on K, these slides. So like we saw, you log in and you load OpenFOAM. I didn't give a version here, so there's a default version. So if I go module avail, I'm not sure. Sometimes you'll see on K, they'll have default in brackets. So if you don't go / it'll just pick a default. But I think there's no default on Sonic. So you actually have to go / 7 or 3.0 or whatever versions there are. So you load OpenFOAM, and then in that, for OpenFOAM, it told us we have to run another command to complete the loading of OpenFOAM. That's fine, and then we can check it works with blockmesh. So then I can either copy over a PITS daily model from my own computer or from a tutorial, or I can set up the case there. But then the critical thing is I have to create a new file called, it doesn't matter what the name is, but it's basically a script file. So it's a file that is going to tell the supercomputer, here's the commands I want to run. So you submit this file or script to the queuing system, and then once it gets to the top of the queue, it will execute the commands you're asking for. So the files, they're sometimes called PBS files. So PBS is the name of the queuing software, but they look something like this. All of these things are the comments. And so these files have a particular structure where they have things that go S-batch, hash, S-batch. So normally hash in a file like this would be a comment, but if it's hash, S-batch, it's a direction to the queuing software. So you can see each one of these is a direction to the queuing software. So in this case, S-batch P dev queue. So this is telling it which queue to submit to, and -n is how many nodes. So both Sonic and K have nodes with 40 cores. So if you ask for one node, you get 40 cores. If you ask for 40 cores. You can't ask for less than 40 cores in K, but you can in Sonic. Then you can say a max job time. So you should just initially try to run it for a very short amount of time, see how far it gets, then based on that, estimate a little bit longer than you think it'll take to run it. What happens if it gets this? Well, it'll just kill your job. Then you can give it job name. So this is in the queue system. It'll appear that if you have multiple jobs running, you might have pit steady 1, 2, 3, 4. And this is a particular one for K. So on K as well, the jobs get charged. Now it doesn't directly cost anyone money, but they're charged CPU hours to a particular account. So you will all be part of the UCD01 account. So UCD01 project gets 100,000 CPU hours per month. So what can happen is near the end of the month, they run out, and that means you can't run jobs. Or you have to apply for your own project. So it's not that difficult if you're doing a thesis project, or certainly if you go to your PhD, you would get your own project on K. So you get your own million hours that you can use whenever you want. And then you can put your email address, so it'll email you when it begins or ends, or you can turn those things off. So these top instructions are for the queuing software. So when you submit it, they're read and interpreted straight away. But then when you get to the top of the queue, which depending on how much resources you're asking for. So if I ask for only one node for 30 minutes, it might start straight away. But if I ask for 1,000 cores for 2 days, it may take a week to queue. So then the commands down here then are to actually run your job. So this will load the software, whether it's Abacus or OpenFOAM. And then in the case of OpenFOAM, I can just say, create my mesh, decompose it, and run in parallel. So you can see here they use srun instead of MPI run on K. And you can see it's putting the outputs into log files as well. So you don't have to do block mesh and decompose bar here. You could have done that first and then just submit the solver, but why not? Just let it be done on the compute nodes. So let me just see. So that's for OpenFOAM for K. We see OpenFOAM for Sonic. So it's very similar. You can see I'm specifying OpenFOAM 7, so maybe I can try this. I can make a file. So it's very similar, but there's an extra option here where in K you have to take multiples of 40. Oh, in this case actually 44 it says. But in Sonic you can actually ask for less than 40. So you can ask for one node but only 4 of the cores. So that would actually just 4 cores I can ask for. So if I do this, so I'll copy through that. So let me just to demonstrate it. So this is me on Sonic. So if I go module list, yeah, OpenFOAM is installed. So if I go to the Scratch directory, which is here, so on that's like the run directory. So it'll be /scratch and then your username, or your username I think would be your shoot number. So get rid of that thing. So I'll go there. See now I'm in the correct directory. I have results here. I actually already have pit steady, but let me make it a new one. MEEN40150. I'll make a directory called the course code. Then I'll copy just one of the tutorials. Obviously, you might actually copy your case up from your own computer, and you can see how to do that in the earlier slides and in the video. So let me see. I can't remember how to autocomplete, so I'm just going to echo that and then copy it. So tutorials, incompressible, simple foam, bits daily, copy it here, go inside it. I'm just going to run block mesh here, why not? me see if we have a decompose par. Nope. So on etc. Okay, you can see where OpenFOAM is installed on the system. I'm going to get the decompose par dict. So it was in pre-processing, I think, or case dicts pre-processing decompose par dict. Put it in here. I think they should have metas on the system. So okay, I'll set it to yeah, I can leave it as 8, and then I'll set it to metas or Scotch, that we can see which one works. And it'll split the case in 8, trying to minimize the processor boundaries. Let me just check. They actually do have Scotch. Okay, so they do have Scotch installed. So okay, I've actually done the decomposition there, but maybe I'll just let the run script do that. So I need to make a file. So the file can have anything here. I'm just calling it run openfoam.ssh or .sh, but you can call it anything. So I'm just going to open a new empty file, and then you can just copy and paste in all of this. If it's handier, let me know. If you want, I can just actually upload this file just in case there's issues with copy and pasting. So job name, I'm going to call it kits daily. I'm going to ask for 1 node, but not the full node, just 4 cores. Actually, we'll go for 8 cores, 30 minutes, should be more than enough. Email me. I don't want to email me here, so I'll just put another hash so that comments it, but I could put in my email address. This is a load of software. It's going to run block mesh, put it in a log, decompose par in the log, run the solver on 8 cores, put that in the log, and then reconstruct the case. So the last thing to do is now, once I've created that script, how do I submit it? So there's command s batch. So if you go s batch, run OpenFOAM, that submits it. So it gives a job ID. And if I write sq, I think, sq, yeah, that will list everything's in the queue. So okay, very few people are actually using Sonic today. So if you want the K, you'll get like pages and pages if there's hundreds of people logging in. But not too many people are using Sonic at the moment. There's normally more than that. So if we see here, we can look for a particular line. I'm using the share partition. That's like the standard one. There's other partitions to do, like special GPUs and stuff like that. Here's the name, my pits there. Here's my username. And then this is the status. So PD is pending. That means it's queuing. This guy's job is queuing. And mine is running. This is how long it's been running. And this is the particular node it's using. So each node has like 40 cores. So it's using Sonic 4. So if I SQ again, this case should be pretty quick. So it's gone. I think I can actually go -u key Cardiff, and that will show just my cases. Very good. So you probably actually recognize names here. I think that's Maliki was doing something. ls. So now all my results are here. So you can see all the logs were created. So this file there. So one other thing here is it produces anything that's not put into a log gets written to a file, which is slurm, which is a horrible word. Slurm dash the name of the job.out. So there's nothing in this case. You can see that the file is 0. Oh, by the way, when I'm typing ls here, I've overwritten that or made an alias so that, like normally if you type ls, this is what happens. But when you type ls-al, it shows all this information. So by default, I have an alias that ls just shows all of this. So you can see the processor directories. If I ls processor 4, you can see it's got the results inside it. The same for processor 3 or 2. If I open up log.decompose par, you can see it decomposes. Open up log.simplefoam. So you can see at the start, it's simplefoam starts with 8 processors. And the way it calls them in OpenFOAM, you have 1 master processor, and then you've, in this case, 7 slaves. So it says here, they're all on Sonic 4, which is the name of the particular node they got assigned to. And then these must be the individual cores they got assigned to. So it runs in parallel. The output basically looks the same as running in serial. And I don't think there's anything at the bottom. Just looks the same. You can see how long it takes. It took 4 seconds. But this case is pretty quick anyway. So running in parallel, I wouldn't expect much, if any, speed up. And then to go log.reconstruct par. What that did is it ran through all the processors and it found any results and then reconstructed them. So it puts the results back in here. So you don't have to do that if you look at the decompose case in ParView, but it can be useful. So now I could just delete the processors. we're done. Yep, so that's the general idea. So you'll see there's only slight differences, maybe in to do with the commands that go to the queuing software between K and Sonic, and also lengths the queues and things like that. I think in K you actually have to tell it the name of the queue as well. You can compare them. And then I've given some instructions here around our descriptions of different things. For example, if you want to kill a job, you accidentally submit it, you can look up the job ID with SQ and then go scancel with kill the job. Yeah, you can have a read through that. And then same with Abacus, will be the same general idea. The only extra comment is Abacus is a restricted software on iCheck, so it means that when you'll see it's there, but if you try to load it, nothing happens. So you actually have to create a ticket through the iCheck support system and ask for, can you provide access to my user account to Abacus? And what they do is they check if you're from a university that has an agreement with iCheck that you're allowed to use Abacus. So usually those, so that's fine. It will, they'll go back to you and say, no, you can use Abacus. I think that might be the same for Fluent as well on iCheck, but Sonic, everybody can use Fluent. But the way you do it in Abacus is you go right click on your job. Instead of going submit, you go write input. That creates a file, whatever your job's called, .input. You find that on your computer, and then that contains all the information about your model. You copy that onto iCheck, the K computer, and then you put that somewhere in its own folder. And then you make one of these files again in SH or PBS file, it doesn't matter the name of it, make it an Abacus. And once again, it looks very similar. This is for iCheck, but for some reason, just some of the settings are a bit more awkward to specify. So you kind of have to always have all of this stuff from here to here to run an Abacus job on iCheck. That's always the same. It's to do with setting up different things that Abacus needs. And just at the very bottom is just the name of the input file. So in this case, job.1. And then this is like this is the command that runs Abacus in parallel. So thankfully, you don't actually have to change the number of cores. The number of cores are calculated by this bit of script here. So it's just up here. So if you ask for one node, it will automatically run on 40 cores. And that's the same idea again. Great. I'm not sure there's anything much more. It's the same idea using ANSYS Fluent, how you export and save the case. There's some instructions how to do that. And then once again, you'll make a system, a script file inside your kind of model directory. And then whether you're running a 2D or 3D with Fluent, there's certain settings you give here. Okay, so that is, I was going to go on to talk about the transport equations, but that's fine. I'll leave it for next week. That when I go through that it'll help you understand things better about partial differential equations, but also help you answer some of the quizzes. I've uploaded these slides anyway, so if you want to go through that. So apart from that, we're all done. So enjoy the weekend. I'm gonna, as usual, hang on. So if anyone has any specific questions for me, I'll stop the recording, but if you want to ask about your mini project or assignments or labs or anything like that, feel free to hang on, and I can make breakout rooms like I've done before where we can just chat one-on-one. So enjoy the weekend anyway, and thanks very much for coming along. Hopefully you found it useful.